we continue. We continue the section 1.4 eigenvectors. Okay. Okay. We have shown that this S lambda is a subspace of Cn, and all non-zero vectors in Sn is an eigenvectors of A corresponding to the eigenvalue lambda. Okay, since this is a subspace, we can think the dimension of that subspace. We define the dimension of this subspace as the algebraic multiplicity of eigenvalue lambda of A. Okay. We say this matrix A is simple if for each eigenvalue lambda of A, if the algebraic multiplicity of lambda is same as the geometric multiplicity of lambda, then we call this matrix A is simple, or it is also called A is non-defective. They are all same. This condition on simple matrix is very important in many applications, including the matrix diagonalization. First note is about the comparison of geometric multiplicity of each eigenvalue and the algebraic multiplicity of each eigenvalue of A. In any case, for any eigenvalue of A, the geometric multiplicity of lambda is less than or equal to the algebraic multiplicity of lambda. It is because suppose we have a geometric multiplicity of lambda is equal to k. Then what that means is we have k linearly independent eigenvectors of A corresponding the eigenvalue lambda. That means we can find a matrix like that, which is similar to A, because we have k linear independent eigenvectors. So we can have the k columns of this in a matrix which is similar to A. What that means is this matrix has eigenvalue lambda of algebraic multiplicity more than or equal to k. So if geometric multiplicity of lambda is k, then algebraic multiplicity of lambda is always greater than or equal to k. Okay? In particular, in a field F, if the field is algebraically closed, if it is algebraically closed field, then A is simple if and only if A is diagonalizable. If and only if condition. If and only if condition. But if this field is not algebraically closed, it may not be true. This is an example. This is similar to this matrix, which is in the set of 2 by 2 complex matrices. But this is the matrix of 2 by 2 of real entries. These are similar in if we have the underlying field F as a C, which is algebraically closed. But if you are in the real, then there is no real matrix S and S inverse that makes this. This S matrix is in Mn of C here. So anyway, since we will talk about the matrices in the in a field which is algebraically closed, as we mentioned. So we start with the underlying field C from the beginning, and we will extend it to the general field with algebraically closed. So now we can say A is simple if and only if A is diagonalizable. If we are dealing with the matrices of complex entries. The next definition. Left eigenvector. You have studied the right eigenvectors before. We defined this the non-zero vector satisfying this condition as the right eigenvector of A corresponding to the eigenvalue lambda. Now we define the left eigenvector of A corresponding an eigenvalue. Let's say Y is a non-zero vector and A is called a left eigenvector corresponding to the eigenvalue lambda of A if Y star A is equal to lambda Y star instead of this. So we generalize the concept of eigenvector from right to the left. Okay, Y star A lambda Y star. So if we think we multiply Y here and Y star here and here and delete this. Okay, that's the definition of left eigenvector. Okay, this is the one main theorem on those two eigenvectors. Principle of bi-orthogonality. If A is an n by n matrix and lambda and mu are both eigenvalues of A that are distinct, in this case, if Ax is equal to lambda x, and x is not an non-zero, x is a non-zero vector, and Y star A is equal to mu Y star, then we can always say X and Y are orthogonal. Okay. If lambda is not mu, if two eigenvalues are distinct, then right eigenvector of one and the left eigenvector of the other eigenvalues are always orthogonal. That's what this theorem says. So the inner product of those two vectors are 0. The proof of this bi-orthogonality property is very easy. So Ax is equal to lambda x from the given condition. We just multiply Y star on the left. Then, since this is a scalar, so scalar can come out without any problem. Then we know mu is an eigenvalue for the left eigenvector y, so we can replace it in this way. Then we can move the term in the right to the left this way. But we know mu and lambda are distinct eigenvalues. Okay? So this cannot be 0. So this should be 0. That says x and y gotta be orthogonal. We told x is not a non-zero vector. Okay. So these two vectors are orthogonal. So left eigenvector of one eigenvalue is always orthogonal to any eigenvectors like the right eigenvector of distinct eigenvalues. That's what it says. Okay. Okay. Yeah. There was one note. Every Hermitian matrix has all real eigenvalues, but some symmetric matrix. This is a symmetric matrix, but this matrix don't have real eigenvalues. It has a complex eigenvalues. See, this is just definitely a symmetric matrix, but the eigenvalues are not real. Okay, there was some note. So, yeah, so this Hermitian matrix in a complex underlying field is a real generalization of real symmetric matrices that you have learned from the undergraduate linear algebra class. Okay, Hermitian matrix is a matrix, this conjugate transpose. Okay, this is a real generalization of a symmetric matrix. Okay, next theorem. Okay, let A and S are n by n matrices, and S is a non-singular matrix, and lambda is an eigenvalue of A, and X is a corresponding eigenvector, lambda. Okay, then we can show Sx is an eigenvector of SAS inverse corresponding to the same eigenvalue, lambda. The proof is so easy. We can just think. Yeah, all we have to show is this, isn't it? This matrix times this vector is same as a scalar times omega, or same vector. That's what we have to show. But as you see, S and S inverse are gone. So we have SAX is equal to S lambda x, because AX is equal to lambda x. Okay. Lambda is a scalar, so this one can come out. So we have this relationship, which says this Sx is an eigenvector of this matrix corresponding to the eigenvalue of A lambda, also eigenvalue of SAS inverse. Okay. There are many things that we can think. But this 1.4.9 theorem is the one that you are learning for new in this class. This is a graduate level theorem and the technique for the proof. Let A be an n by n matrix, and K is a positive integer, and lambda is a scalar. Let lambda is an eigenvalue of A, and geometric multiplicity of lambda is greater than equal to K. Then we have the following two facts. The first one, if m is greater than n minus k and alpha is in QMN, that means alpha is a sequence of integers which is chosen from 1 to n and with m numbers in it. Okay, then that eigenvalue lambda is also an eigenvalue of this submatrix, this m by m submatrix. This because this is the size of alpha. Okay, so okay, yeah. This is also this part A also can be shown by the knowledge that we have. Suppose we have a geometric multiplicity of lambda is equal to k. What that means is A is similar to which matrix? Lambda ik times 0 times. This is what I mentioned earlier. If we have a geometric multiplicity k or greater than equal to k, then we have linear independent eigenvectors of A corresponding to the eigenvalue lambda more than or equal to k. So this first part, the proof of this part also comes from this fact that I already mentioned. Then, for this alpha is chosen in that way. So if the length, if m is greater than equal to n minus k, what that means is if you delete some part of this, still you have some lambdas left. That means lambda is an eigenvalue of some of this. Because some lambdas should be included in this submatrix, isn't it? This is n by n, this is k by k. So if this n minus k is big enough, then it should include some part of lambda here. That means lambda must be the eigenvalue of this. Okay. Okay, but important part is this. This is just the lemma that we can use. This is the important thing. The second part. If geometric multiplicity is greater than equal to k, then algebraic multiplicity of the same eigenvalue also should be greater than or equal to k. That means algebraic multiplicity is always bigger than or equal to geometric multiplicity of the same eigenvalue. We have to show this part, and we have to use it a lot. This is a basic knowledge for anything on diagonalization and also Jordan canonical forms and everything. All of the canonical forms are using this fact. Many theorems, many problems are using this fact. So technique of showing this fact is just use the first part of it. Okay? Yeah, we now know the first part. Then we use it to show the part B. Okay. First, you may recall one exercise that you have shown. It was one of the homework problem for you. Who was assigned this problem? I think it's you. And also it was covered in our class. I gave a proof of this one in last lectures. Okay, let's just recall this. Suppose AI is just n minus 1 by n minus 1 submatrix. Then determinant of the characteristic polynomial of A is a summation of the characteristic polynomial of this n minus 1 by n minus 1 submatrix. we will use this for the proof. Okay, yeah, we have shown that this way. And we will show that we'll use that fact in the proof of the part B. So we want to show geometric multiplicity of lambda is always less than algebraic multiplicity of lambda. This is what we want to show. This is part B. Okay. When this one is greater than or equal to k, we want to show this one is greater than or equal to k. Okay. Let's start. Suppose the geometric multiplicity of lambda, which was k, is equal to 1. What happens? From the first part, m is greater than or equal to n minus k, which is 1 now. Then we know m is equal to n. M is always less than or equal to n. Okay. So if this is bigger than n minus 1, is bigger than n minus 1, then it's got to be equal to 1. Then what it says? Alpha was chosen from Q, M, and N. That means and N. We chose every column of the matrix and every rows of the matrix A was chosen. That means lambda is in this matrix. Lambda we called sigma of lambda of this and this. Okay? But we have everything in there. So alpha is just everything. So lambda is an eigenvalue of it. What that means? Algebraic multiplicity is greater than or equal to 1. Okay. We have eigenvalue. So algebraic multiplicity. Algebraic multiplicity means it's just the number of roots in the characteristic polynomial of the given matrix A. Okay. Next case. Suppose if k is greater than 1, then, yeah, we know from this condition, we can think first m is greater than n minus 2. We know it from there. In this case, there are two cases. Sub case 1. M can be 1 or m can be n minus 1. There are two cases. Isn't it? That's the only case if n is greater than or equal to 2, because this cannot exceed n. So there are only two cases. Sub case 1, sub case 2. For this case, it's done. We have proved it. Then eigenvalue, there's lambda is an eigenvalue. Next case. If m is equal to n minus 1, what happened? Then we know this fact. Isn't it? Yeah, from the exercise. From here, we can think the n minus 1 by n minus 1 submatrix. Then think the characteristic polynomial of A, I. Okay. Then, if n is equal to n minus 1, then from here, if m is equal to m is equal to n minus 1, what that means is this is like this. This is n, this is n minus 1 by n minus 1. Every arbitrary matrix of alpha, because this alpha chose arbitrarily with these conditions. So from the part A, we know lambda is an eigenvalue of any n minus 1 by n minus 1 submatrix. So it satisfies the characteristic polynomial of the n minus 1 by n minus 1 submatrix of A, every one of them. So we know this by A. So each of these are zeros for lambda, so summations got to be 0. That means the derivative of the characteristic polynomial of A at the value x is equal to lambda is equal to 0. But that means is lambda is a root of the first derivative of characteristic polynomial. What that means, the algebraic multiplicity is greater than or equal to 2. You understand? PA of lambda was 0 and PA prime of lambda is equal to 0. What that means? It has a eigenvalue of algebraic multiplicity more than 2 or equal. Okay? This shows this. Okay? Because algebraic multiplicity is just the number of roots in the characteristic polynomial. Understand, Horror? Okay. Hannah, understand? Okay. Then, now we think the case k is greater than 2. Then we still use the part A of the theorem. If m is greater than n minus k, then for the case m is equal to n minus 2, then we should think the second derivative of the first one. But we know already PAI of prime of lambda is equal to 0 for each I from 1 to n, isn't it? From the beginning, if k is greater than or equal to 2. So we now think this. This is summation of this. Okay? But let's think. The summation of first derivative of all this. That now we think this is the first derivative can be written in this way by the exercise. Then this matrix is a submatrix of this size. Okay. Now, for the case m is equal to n minus 2, we know lambda is an eigenvalue of this matrix from A. Okay, submatrix. What that means is this lambda satisfies that characteristic polynomial of all of this size. Since all these are 0, the summation of these are 0 at x is equal to lambda. What that means is the second derivative of the characteristic polynomial of A is equal to 0. So we can think the first derivative, the lambda is the root of the characteristic polynomial. It is also the root of the first derivative of the characteristic polynomial, and it is also root of the second derivative of the characteristic polynomial. That means the characteristic polynomial has a root as a lambda more than 3 times. We just continue this argument. Then for each derivative, A is else derivative of characteristic polynomial of A, then we can show each of them are 0 at lambda for each L from 0 to up to k minus 1. From there, the same argument shows if k is greater than or equal to k minus 1, we can show algebraic multiplicity of lambda is greater than or equal to k, which says algebraic multiplicity of lambda is greater than or equal to k, which was the geometric multiplicity of lambda. This technique of the proof are using this fact. Now you can prove this important fact since you know this important lemma that you can use, as well as the first part of this one, which has a beautiful similarity facts that you can use in order to prove the first part of the proof. Okay, now you have this. Algebraic multiplicity of each eigenvalue is greater than or equal to the geometric multiplicity of each eigenvalues. Okay, that's it. That's the end of the chapter 1. There are some problems in page 61. You may try these 5 problems, 1, 2, 4, 5, 7. Jin, you may try the first, and Hana may try number 2, and Horror, you may try number 4, and Mr. Jung, try number 5, and Mr. Jin, you may try one more, which can be 7, about the power method, or some facts on the right eigenvectors. You can just choose 7 or 10. Okay, that's it. That's the end of the chapter 1. Do you have any questions?